So last time we finished chapter 2, so we finished up section 2.8. What I've put up here together is, or put together for you guys, is just a little bit of review stuff. So I'll start with just talking about the test format, right? The test is next class, so that's Monday. So you have one question where you have to use a table to estimate the slope of a tangent line. That's like a 2-1 question. One question, use the graph that I give you to evaluate some limits. That's like a 2-2 question. One question, make a table of values to estimate a limit. Another 2-2 question. 3 questions where I ask you to use your calculator to graph the function to estimate the limit. Kind of like another 2-2 question. 4 questions where I ask you to evaluate the limit using algebraic methods. This is like 2-3 through like 2-6. Kind of all those methods are all scattered throughout there, but you have finite limits. You could have limits at infinity. You could have infinite limits. You could have some of the tricks where you have to multiply by a conjugate, or make a common denominator and add 2 fractions, or simplify by expanding. Any of those kind of tricky things that we've done to get around the indeterminate cases. 4 proofish questions. You only have to do 2 of them. You can choose to do whichever 2 you'd like. The topics will be on like squeeze theorem, intermediate value theorem, and continuity. So again, it'll be like prove that this function is continuous at this point, or use the squeeze theorem to do the limit, to do this limit, or show that this function takes on this value somewhere on this interval, like an intermediate value theorem question. Stuff like that. None of them are super involved proofies, but they're like things we should be able to do. They'd be like a standard part of a multi-part free response AP question. These are all kind of things that I expect to see. One question where I ask you to find the discontinuities on a piecewise function. One question where I ask you to sketch the graph of a function from information about its points and its limits. So again, I give you we've done homework questions like this, right? Where f of 2 is equal to f of 3, which is 7, and then the limit as x approaches 4 is infinity, or a question like that where you just have to kind of sketch it out. One question will be like a derivative story problem. That'll probably be motion related. So position, velocity, acceleration kind of question. One question where I ask you to use the graph of a function to sketch its derivative. So we did that in the homework, I think in 2.8. There's several questions like that in there. And then one question where I'm asking you to use that definition of a derivative to do some stuff. Again, that's like a 2.8 question there. And then I put together a list of problems from the ones that we've already assigned. So this is, when I was going through and I was writing the test, these were kind of the problems that I looked at as inspiration for what I wrote. So I've gone and narrowed down from hundreds of problems down to, 40 or something here to look at. So that should help narrow your focus when it comes time to start doing your preparation. And then there's some important definitions and theorems that, again, you'd want to make sure that you really know and understand, because they'll be part of instructions and things you'll have to use on the test. So definitions, continuity. So not only continuity at a point, but on an interval, and then left and right continuity, making sure that we understand what those things are and how to show that something is one of those. Asymptotes, so the limit definitions for a vertical or horizontal asymptote. The definition for a derivative. And then differentiable. And then our important theorems that you'd want to make sure that you know so you're able to use when asked for them. So the squeeze theorem, intermediate value theorem. As part of that, you'd also want these continuity theorems to know on site what functions are continuous. And then like that the addition, subtraction, multiplication, division of continuous functions is continuous over their codomain. Stuff like that. And then that differentiable theorem, that if a function is differentiable, then it's continuous on that interval. Okay, so those are, in terms of study preparation stuff, I think that's pretty comprehensive. Yeah, check.
Will we get the derivative equation, or will we probably memorize that?
Yeah, so here's the thing. The AP exam, the equation sheet is a blank sheet of paper. So like stuff like that, you need to memorize, and like we better start now because, you know. So again, I ordinarily, if it was just me, I would say like I don't really like wasting a lot of time memorizing things, but like AP expects it, so like I'm gonna continue to kind of wrap things in that are stuff that like we should have memorized, and then gonna kind of hold that same expectation. So that's certainly fair question though. Like I need to know, do I need to memorize this or not? Those are important things to know before you start studying. So I have no problem answering any of those. Like, do I have to have this memorized? Like, how good do I need to know this kind of thing? And I'll be very frank with you in those sorts of situations. Okay, so that's kind of the test in a nutshell. I didn't write a test-specific review because I gave you the homework problems that I was kind of drawing from to write my test questions, which I felt like was going to be pretty equivalent to any study guide I would have been able to write. And these have the added bonus of being things that we've already kind of talked about, that you have some idea of like what the trick was and that kind of thing. So I felt like that was going to be equivalently useful for you. Does that seem fair to you guys?
Yeah.
Okay. I think if you add up the math there, I think there's 19 questions. So you only have to do 17 of them. And I know that sounds like a lot. And if it becomes too much, we can figure that out after the test. Again, I've taught this course before, but it was like 15 years ago. So remembering kind of what the expectation is, we'll figure that out. But I think when I did the math, it's like 4.5 minutes per question at 17, which didn't feel bonkers to me, considering some of these should be pretty quick. Like to sketch the graph or, of the derivative from the function, or like use the table to estimate the slope, or some of these things are probably going to be pretty quick. And none of the questions in here are like super heavy involved where it's going to be like a page of doing stuff. And if I'm wrong, then we'll deal with that, and we'll come up with a fair way of, if I just way off, and we'll do better next time. But Mr. Gulick's not an insane person that's like, oh, class average was a 63, everybody gets an F. Everybody's had me in class and knows that I'm not like a crazy person like that. But I just want to make sure that we talk about it beforehand, so you get to the test and you're not like in absolute panic mode. It's like I had 3 blank pages at the end or whatever. It's like, okay, so we can talk about it some more after that, if that is what's happening, or multiple people have like multiple blank pages or whatever. Okay, cool. At this point, if you guys have homework questions on stuff, we just finished 2.7 and 2.8 yesterday. I don't know if you guys have stuff's come up from there that you want to talk about, or if there's old stuff that you're like, hey, I know this thing from way back here I didn't feel good about, but we'll take some time here to do that. After we finish with these questions, I did make up some more AP multiple choice questions for you guys to practice on, just as like a homework assignment. It's not like a quiz grade or whatever, although I would care about right and wrong to some extent. Like it'll be banded or whatever, like we've done before, where you get like 2 or 3 wrong and it's still full credit or whatever. Does that feel okay? Yeah, that would be due Sunday at I think I set the due date on that multiple choice at like 11:45 or something p.m. So it's basically the same time as the problem set. But realistically, I think I had 15 problems on there or something, and last hour, most people seemed like they burned through 10 of them in half the class period, working together and just kind of talking things through. They weren't going particularly fast, so I don't think that'll be a big time suck on you. Again, I'm not trying to be, like there are things that I think should help studying also. So I tried to pick things specifically that we haven't talked about a lot, that I thought were relevant to the things I was asking you to do on the test. So I'm not trying to be like loading everybody down with a million things to do, but I think it'll be helpful or serves a purpose, right? Okay. Homework questions. Luke, I saw your hand.
Do you mind just running through 47 on 2.8?
Yeah, sure. 2.8, number 47. All right, let's do this. I'm going to do, I think I'm going to start doing this. Oops, not yet. 165. You said 47, right?
Yeah.
Okay. I'm going to start doing these screen clippings, I think, for the homeworks, because I think it'll just be kind of easier for everybody. All right. Use the definition of the derivative to find f prime, f double prime, and then graph them on a common screen and check if your answers are reasonable. Okay. I'm probably going to skip the graphing part. Yeah. Okay. So just going to use my standard definition for a derivative. So remember, we had two versions of this. This is the one I most prefer. So plugging things in. So I'm going to have 3 times x plus h squared plus 2 times x plus h plus 1 minus 3x squared minus 2x minus 1 all over h. So I distribute that negative through on the f of x. Okay. I'm going to go ahead and simplify now through the numerator. So I'm going to expand and FOIL here. So 3x squared plus 6xh plus 3h squared, 2x plus 2h plus 1, and minus 3x squared minus 2x minus 1, all over h. Now I'm going to combine some like terms. The 3x squared and the negative 3x squared cancel each other out. The 2x and negative 2x and the 1 and negative 1 all cancel out. And then I notice that everything that I have left contains a factor of h. So I can reduce. And that'll get me to the limit as h approaches 0 of 6x plus 3h plus 2. And when I apply direct substitution to evaluate that limit, I get 6x plus 2. Okay. And if I want then f double prime, this piece.
Oh, you just crossed the h.
Yep, just the h. Just the h went away. The nice part is that everything gets a little bit simpler now, because the function that f prime is way less complicated than the function was for f, which I'm super excited about. So that's going to be 6 times x plus h plus 2 minus 6x minus 2 all over h. But what I forget to write there? Yeah, you're being bad, Mr. Kulik. Can go ahead and distribute through the 6. And then if I combine my like terms, 6x and negative 6x, 2 and negative 2, and then everything left contains a factor of h, reduce those out and do the direct substitution, I just get 6.
Yeah, I think I just like messed up.
Okay. That's, yeah, it's not uncommon. Like these ones can get pretty messy. And if you goof up one little thing, you know, like you FOIL something out, but you forget to distribute everything through, you end up with something that doesn't cancel that needs to cancel. And now you're left with like, I still have an x term, so I can't reduce the x or the h's because I have something with just an x in it floating around in there, which hopefully at this point is like an indicator that like, okay, just made an algebra mistake, just back the truck up because all of this stuff needs to cancel out so I don't have any h's or the only things left in the numerator have to have h's in them so I can reduce. So I've just made an algebra mistake. I just need to back up and, you know, be a little bit more careful or whatever on the previous step or two. But that should happen every time when we do this. Paul.
I just kind of have like a concept question that fits perfectly with this. Because you take x to the third that's here.
Mm-hmm.
It's like I get confused when it like I think it's supposed to equal 0, but I kind of like get confused summing stuff. And I think it's like I just wasn't like I kind of zoned out.
Yeah, that's okay. So this would be our setup, right? Okay, when I do this, I get 6, I need to put limit, which approaches 0. So when I do, if my f double prime is just 6, f of x plus 6 is, or f of f plus h is just 6, right?
Yeah.
And I have that. So I have 0 over h, which is just 0. And if I evaluate the limit of a constant, it's just a constant.
Oh. I think I kept trying to do my substitution of.
Yeah, if you try to direct sub here, yeah, you get indeterminate. You have to reduce that fraction first before doing the limit, right? Because 0 over h is 0. So we're good there. Is this a follow-up to this one or is it new?
New question.
Okay. Luke, is this a follow-up?
It's like a side tangent about the question.
Okay.
So if you were looking at a distance time graph and that was your line, the 6x plus 2,
Okay.
then 6 would be your velocity, right? Or will it not be because it has to...
Well, I would say this guy would have been position. This guy then would be velocity, and this guy would have been acceleration.
Okay.
So typically, whatever we start with, you'd consider the position function.
Forgot about that.
Follow up, Jillian? Okay. Blake, you're next.
Yeah, don't worry.
Okay.
Sorry, Blake. In the context you asked us to find the derivative of the constant, do you want us to show all that work, or just remember the rule that any constant's derivative is always 0?
You should probably, I mean, at this point, I would expect you to show this.
Okay.
Although, like, you're clear that we know what we should be getting. I guess the directions would matter, right? Like, if I ask you to show algebraically, you know, like, then yes, I'd want to see this. If it's just like, what is the derivative, and there's no direction given further, I'd say, yeah, you can just write 0. Blake.
So how do you, so for number 51, so how do you like multiply the conjugate for this?
Yeah,
I don't understand like
this
what
is
I'm supposed to
this
do.
is a swell question because the trick here is very tricky. Because what we're not going to do, guess what we're not using? A conjugate.
Oh.
Ugh. And
got me there.
yeah. So this is a good one to ask about because, like, okay, if I'm not multiplying the conjugate, like, what is the trick? And everybody get ready as we do this, because it's a good one to see. All right, so part A says if A does not equal 0, use equation 2.7.5 to find f prime of A. So one little quick side note here. It's saying that A cannot equal 0. Did you wonder why?
Look at number C.
Yeah, if you look at C, says that like show that there's a vertical tangent line there, which, okay, so the derivative can't exist at that point. That's why they're not letting us include that one, so that when we differentiate this, we don't have to worry about like restricting a domain anywhere. We can just write it. Okay, so this asked us to use the alternative formula.
Is that what 2.7.5?
Yeah.
I couldn't find that equation, so.
Yeah, it would have been in section 2.7 and then equation number 5. So it would have been there on page the bottom of page 146. It would have been a red box with a 5 next to that formula.
Oh yeah, you're right. My
Yeah.
bad.
No, it's
I tried looking it up like on the book on the internet, like using Control F for 2.7.
and then you found like too many things, right?
Yeah, exactly.
Yeah. And in fact, it's not labeled that way
Yeah,
on there to find it in the PDF. Yeah. So that's how the book is. So it's like chapter, section, and then like equation or whatever is how that's set up. All right, so we do this. We have the cube root of A minus the cube root of X over X minus A. And Blake's question was like, okay, how do I use what's the conjugate here? And I wouldn't do that, because why wouldn't I use a conjugate in this case? It's a cube root and not a square root. Because if I multiplied this by like the cube root of A squared minus the cube root of X squared to the top and bottom, I'd have to FOIL the numerator out, and then I'm going to get a bunch of stuff that I don't want along the way. So here's the trick. I'm going to look at that denominator, and I'm going to see the denominator as, instead of x, I'm going to think about it as the cube root of x cubed. And instead of a, I'm going to think about that as the cube root of a cubed. Everybody's cool with that I can do that, right? That's why is this going to be helpful, Mr. Kulik? Well, do you remember the difference of two cubes factoring pattern?
No.
Yeah,
Sorry.
That's okay. It's been a long time. So that's what I'm going to use there, is the difference of two cubes factoring pattern. Because if I look at the numerator, what is the numerator? Yeah. Oh, I think that this also, I goofed this up here just a little bit. So this was supposed to be x minus a. I just had this stuff in the wrong order. I'm going to end up with an extra negative sign if I didn't fix that. Okay. So let's go ahead and do that factoring.
Would it be root 3 2ax or just ax?
Just ax. Oh, yeah, because that's not supposed to be a 2 there. Great googly moogly. This is supposed to just be ab. Yeah, thank you. Thank you. That's a big oopsie, Mr. Kulik. Well, you know, like, I did it right when I used it. I just wrote
Yeah,
it
you
down
did.
wrong. Which, yay. Okay, so we see now why that difference of two cubes factoring pattern was quite useful here, because it's going to allow me to do that reducing. Which is great, because that was the part that was giving me the zeros. And now if I direct substitute, I just have 1 over cube root of a squared plus the cube root of a squared plus the cube root of a squared, which is all 1 over 3 cube roots of a. It's a dirty trick, Mr. Kulik, needing to use the difference of two squares there. Or two cubes, excuse me. I said the wrong thing there. Should we go on and do parts B and C also, Blake? As long as we're at it.
I didn't get that.
Yeah, I mean, if you didn't get this, there wasn't much else you could
Yeah.
do, right? You kind of needed to be able to do this, so.
Uh-huh.
All right.
Would it be the cube root of a squared? Or
Oh, yes. Thank you. Yep. Thanks, Paul. Yep. Everybody's cool? Alternatively, just FYI, hopefully from Algebra 2 you would remember this, right? That those are all mean the same thing. So again, if depending, you could have written your answer a bunch of different ways there and it still would have been okay. And I wouldn't bother rationalizing the denominator here or anything. Like, don't bother with it. I think our days of rationalizing denominators are done. So, unless it like serves an algebraic canceling purpose, but if it's just for the sake of like, your answer shouldn't have a radical in the denominator, I don't think we care about that anymore. It does not appear that the AB cares about it on the multiple choice stuff. And I'm going to tell you is that it quickly became apparent that nobody cares about this after you get far enough into mathematics. So I think we're far enough now that I don't think it matters. Now, certainly you could do it and it's not wrong. I would not advise doing it because it's just like one extra thing to goof up. All right. Part B then says, show that f prime of 0 does not exist. Okay. Well, let a equal 0. So I'd have f prime of 0 equals 1 over 3 times the cube root of 0, which is equal to undefined. So I can say then f prime of 0 does not exist. Or I would say, let's say it this way. So 0 is not in the domain of f prime. Therefore, f prime of 0 does not exist. What else could you have done there?
Whole formula thing.
Yeah, so you could have done this.
Although, why would you use that formula instead of the other one?
Well, the directions told you to do that for one. That's mainly my answer. The drawback of doing it, trying to do it the other way, is then you would have absolutely had to multiply by the cubic conjugate if you'd use the one with the h in it, because there's no difference of two squares or difference of two cubes staring at you to try to use, which good luck coming up with the conjugate for a cubic, because it's this thing.
Oh, okay.
But like, woof, coming up with that on your own would have been a big ask, as opposed to thinking about it the other way, where it's like, oh, this is a factoring problem. I know how to do this conceivably, I would have known how to do this factoring. But you do it the other way, and then you're stuck multiplying by the conjugate, and it gets kind of bad. Okay. So I would need to do this both ways, right? To show that the limit goes to different values, so the limit doesn't exist, so the derivative doesn't exist. So I'm going to simplify all the way down to here that we used before. Everybody's cool with that? So this, if I'm approaching 0 from the left, that's going to be a negative number close to 0. When I take the cube root of it, I'm going to have something negative on the bottom that's also very close to 0. That should be going to negative infinity. Everybody's cool? And then if we do the same thing over here, but we're going from the right, it'll go to positive infinity. Taken together, I can say the limit as x approaches 0 of this thing does not exist, since the right-hand limit and the left-hand limit are different. Everybody's cool with that? You could have also said that. The added bonus of doing it this way is that it answers part C, where it says to show that the cube root of x has a vertical tangent at 0, 0. So you're basically looking at the slope of the tangent line at 0, which is exactly this. To show something's vertical, you'd show that either the left-hand limit or the right-hand limit or both go to either positive or negative infinity, which is exactly what we did there. So that would count as our answer for part C as well, which is nice. You'd have to do a little bit of lead-in as to why this limit going to positive or negative infinity tells you it's a vertical tangent there, but it's like a sentence, right? That the slope of the tangent line at 0, 0 is going to be the value of f prime at 0. And then you can show this. And it's like, oh, look, that's what I need for a vertical. Does that feel okay, Blake? Okay. So the big trick was using that difference of two cubes and using the correct, or using the indicated derivative formula.
Okay.
What else do you guys got? Again, happy to do others. If there's older stuff, it doesn't have to be just 2.8 stuff. If you have other things that you want to talk about, or if you have more 2.8 and 2.7 stuff, that's definitely okay too. Well, I want to do one that I thought was a good one. I want to look at 9. Yeah.
Your equation that you use for like part where you're doing part C,
Mm-hmm.
that's bit, all that's just like the alternate.
That's the alternate form for a derivative. Yeah, that was equation 2.7.5 that they referenced in the question. That's why I was using that version. Is it made this particular problem a bit easier to deal with. Okay. Okay. So the directions for this problem just ask to, this is our function f of x, wants us to sketch the graph of the derivative. Okay. So the first thing I'm going to do is look for any place where the derivative might be 0. What are those going to look like? They're going to look places where we have a horizontal tangent line. So extrema would be a good example. Now, this problem also has extrema, but is the derivative equal to 0 at these extrema? No. Yeah, because these are corners. What is the derivative equal to at a corner? Undefined. It doesn't exist. Everybody's cool with that? So I know at those 3 specific corners, we're going to have an open circle when I draw our graph. Everybody's cool with that? And there's no other place where I have a maximum or minimum. I don't have any extrema there, so I don't have any other place where the derivative could be 0. All right, fair enough. So I'm just going to start looking from left to right at each of these sections of my graph. So if I look at this first section before the first spot where I know that the derivative is undefined, that graph is decreasing, right? The slope there is negative when it's decreasing. And I notice that's a straight line. So what is the slope for a straight line? Constant. So I know this is going to be a constant negative value. And it's not very steep, so I'm not going to make it like super low. I'll just look like that. Everybody okay there? Luke, you look upset.
This is like just like, this is what we're doing in physics.
That's awesome. You should feel really well prepared then, right?
I'm feeling pretty good.
Good.
Bring it up together.
And then
I'm still doing Ivy Bio.
Yeah, no, that sucked.
I'll look at the next section. I notice that that piece is increasing, so I know the slope is positive there. And it's a straight line, so that's a constant positive slope. And that section looks a little bit steeper than the previous section to me. So I'm going to make that a little bit higher up than, or a little bit further from the x-axis than the previous negative section. Everybody's cool with that? And again, I'm using all open circles at these boundaries because at each of the boundaries is a corner. Go look at the next section. So that's decreasing, so it has negative slope. It again is a straight line, so I know the slope there is constant. And that looks the same amount of steep as the previous one, so I'll go like the same amount away from the x-axis as my previous piece. I'll do that. And then I'll look at my last piece, which is increasing. So it's going to have a positive slope. It's a straight line, so that slope is constant. That slope looks to be about the same steepness as that piece in yellow. So I'll try to make that about the same distance from the x-axis as I did the piece for the yellow. And I'll just draw my section and I'm done. Does that feel okay with you guys? Again, I think there's definitely a question where I ask you to do this kind of thing on the test. It may not be all straight pieces, so it might be like something that's actually continuous. But here we shouldn't be surprised that the derivative has got a bunch of discontinuities in it, since we see all those places where the derivative doesn't exist, all the corners. Cool? Okay. What else? Jack?
Number 14 on 2.7.
2.7, number 14? Sure. That's a good one. Let's see, that's page 151. And again, I think I'm gonna steal the question. Oh, I meant to do this. Gonna screen clip that question because that's a lot of words there. All right. If a rock is thrown upward on the planet Mars with a velocity of 10 meters per second, its height in meters after t seconds is given by the function h equals 10t minus 1.86 t squared. Find the velocity of the rock after 1 second. So this is basically just asking for h prime of 1. Okay? So I'm going to do my just definition of a derivative. So this is going to be, and then I'm actually going to do, I think I'm going to do part B first, because after I do part B, I can just plug in 1 for A to my equation that I get, and I'm just going to, that feels like easier to me.
Yeah.
To just do it in that order. Mr. Kulik is always super annoyed when we want to do it this way, where it's like, oh, do it the specific way and then do it the general way. It's like, no, can I do it the general way first and then use that to do all the specific ways after? Yeah. I think they do it this way because they think it's going to be, for some reason, like harder to do it the general way or something. I don't know. It's like the same problem. It just got, one has numbers in it and the other doesn't. Except that should be a plus. Everybody good here? I'm going to distribute in FOIL now. It's going to be 10a plus 10h minus 1.86a squared. If I multiply that by 2, that's going to be 372, I think. Does that sound right to you guys? Okay. Yeah, and if you, no issues if you're wanted to double check that math. That's kind of why I asked. But I think that's got to be right. Let's see. Now we'll great. My brain still works. Cancel the common or the like terms. Now I notice that everything left has a factor of h in it, so we can reduce. And when I do my direct sub, when I plug 0 in for h, that last term just drops off of there. So then if I want to do h prime of 1, I can just do that, which feels like, oh, that's way nicer, Mr. Kulik. Yeah, man. Work smarter, not harder. And this is going to be meters per second, since heights were in meters and times were in seconds, and this is the derivative, so it's a rate. Part C says, when will the rock hit the Earth's surface? So there we're talking about position or velocity? Position. So I'm going to use the original function. So the height should be 0 when it hits the Earth or the Mars's surface. To solve this, I'm just going to factor. So I can take a greatest common factor of t out. When I set each piece equal to 0, I get t equals 0, but that's not the answer I'm looking for, right? That's the initial state where a rock is sitting on the surface or whatever. So I get 10 divided by 1.86, whatever that comes out to be. $5.38-ish. And then in part D, it says, what will the velocity be when the rock hits the surface? I need to use the derivative there. And what value of t am I plugging in? 5.38. Which again should be easy to do now, because all I have to do is plug it into that derivative formula. I don't have to do another limit, which, yay, becomes pretty easy. The trick here is just to make sure you're using the correct function, right? Like, when should I be using the derivative and when should I be using the function, or the position function, when should I be using the velocity function? So that's about negative 10.01. And that's, again, meters per second. Does a negative answer make sense here? So it's, yes, exactly. Since it's a velocity, the rock should be falling down when it hits the surface of the Earth, or of Mars. So that makes sense to me. And I noticed that the force that I threw it up with, 10 meters per second, is almost exactly as the same force that it's falling down with, or the speed, I should say. Why is it not exactly 10? I rounded there. Yeah. If I'd used 10 over 1.86, I think I would have gotten exactly 10. Tegan?
So part C, why didn't you use the derivative?
So it asked, when will the rock hit the surface? So that's asking about a position, right? Where is it located? That's a position function question, not a speed question. Does that, and that's the trick of these kind of questions, right? Is making sure you're using when to use the function, when to use the derivative or second derivative or third derivative or whatever it is you're working with. And again, that's a common thing that students struggle to kind of keep straight, is when should I be using the derivative and when should I be using the original. Anybody else? Yeah, Teagues.
Can you just do another drawing the derivative of just like a normal function?
Yeah. So that was on, all those questions kind of came from 2.8. So that was on, a bunch of those were on page 162, if you're following along. I'm just going to do like 4. That's okay with you. That's a pretty standard looking thing. Right? Looks like any old whatever. Ooh, make it big. So I'll draw this in red. So if I look at this, again, the first place I'm gonna look are for places where the derivative is 0. I see 3 of those, right? I see at this value of x, at this value of x, and this value of x, the derivative should be 0. Okay? I don't see any place where the derivative is gonna be undefined. So I know I don't have to worry about any discontinuity here, right? Because I know if the derivative or the function is differentiable everywhere, then it's continuous everywhere. So since I see no places where I would get an undifferentiable, that being a discontinuity, a vertical piece, or a corner, those are the 3 things I'd be looking for. I don't see any of those, so my derivative should be continuous the whole way through. Now I'm just going to look at section by section. So this piece is decreasing, so it has negative slope, but it's curved, so the negative slope is going to be changing at each piece. I start out, if I draw like the tangent line, that's like the steepest place, almost vertical. If I get down to here, it gets pretty shallow. So I'm going to start very far away from the x-axis and get very close to the x-axis as I go, and it's just going to be kind of curving, I think. So maybe like that. Get you out of there. And I'll just stick an arrow at the end of that. Okay there? I'll look at the next section, which is this piece. There I notice that the graph is increasing, so it has positive slope, so my derivative should be above the x-axis. But again, it's not a straight line. If I look at this, the derivative is pretty shallow. Starts off kind of shallow, gets pretty steep, and then it gets pretty shallow again. So I'm going to be starting close to the x-axis, getting to a maximum, and then coming back down to the x-axis, right? Now, do I have any idea of like where that how high that maximum should be? No. There's no scale on the graph. There's nothing you can do to like, you know, more to estimate it. All Mr. Kulik's going to be looking for is that like the zeros are in the right place and the stuff is on the right side, the correct side of the x-axis is basically all he can look for on a problem like this. Next section is this one. Decreasing, so I have a negative slope, so I'm going to be drawing my derivative below the x-axis. Again, the slope starts pretty shallow, gets pretty steep, gets pretty shallow again. So I'm going to have something that looks basically identical to the other section that I just drew, except it's below the x-axis. Bless you. And then we have this piece here, which again I see a positive slope because it's increasing. So I'm going to draw my derivative above the x-axis. I see it's curving where the slope is getting steeper and steeper and steeper as I go to the right. So when I draw that piece, it's going to just kind of be going steeper and steeper and steeper as I go to the right. Does that feel okay, Teagues? And again, these couple that we've drawn are, I think, pretty representative of kind of the thing that I would give you. I would give you something like cuckoo crazy, where it's got like a bunch of pieces and like asymptotes all over the place and it's all wacky and kooky. I'll give you something that's like pretty doable, right? Something, I think the last two are both pretty representative of the amount of complexity I would expect from a question like this on a test. Does that feel good? These should feel pretty doable, right? There's not much to do here other than like thinking a little bit about where stuff needs to go, but there's no calculation to do. It's just all conceptual. All right. Anybody else? Okay. If you change your mind, yeah, Luke.
So for the neon green section. So positive slope, so you're going to be above the x-axis. And so then as you're increasing and getting steeper, you're going to be drawing your line up. But then as you're reaching like a constant, that means your other graph is going to have a peak. Right?
Yeah, so here's what's going on. Like I start off pretty shallow so that we're close to the x-axis. Gets pretty steep, I'm far away from the x-axis, and then we end up shallow again, so I have to curve back down to the x-axis.
Okay.
Right? Does that make sense if you think about it in terms of tangents?
Yeah.
And if you need to do that on the graph to like make sure you're doing it right, please do that. That's like if you were going to count something as showing your work, that would be like how you could show your work is draw in some of those tangents so that you're like, okay, you know, this is what the slope looks like at this point, and this point, and this point. So like little, big, little, you know. All right, I'll stop the recording.